All right, so this is essentially part two, or it's lesson two in unit four, but it's directly linked to lesson one. Lesson one was spending more of our time on all the atomic models, but we ended that lesson talking about the spectra and the Bohr energy level, or Bohr orbitals, pardon me. So that's what this lesson is going to go into in a little bit more detail. Um, and I promise it won't be as long as the last video. um, I apologize for that. It's funny because when we're in class, I can go for like 80 minutes and lecture you. And here, that one was like 38 minutes, and I'm like, oh, this is getting long. So it's funny how this is making me, you know, realize some things and maybe make some changes as well too. So anyway, at the end of the video, the last part where we talked about, we said that if we excite gas, we heat it up, it's going to cause the electrons to move to a higher energy state, but then they're immediately going to come to lower energy state. They're going to fill those lower energy states that were opened up, right? And when they move to lower energy states, they're giving off energy. Some of that energy is in the form of visible energy, and so we can see it. So this is our hydrogen, and we can heat it up. So this here is just a gas discharge tube. And I'm going to make a little video after this of one here that I have it's a demonstration I do at the school. I brought it home here and I'm gonna show it to you. But basically we just heat up the gas and it looks like a single color. We put a spectroscope on it and then you can see the other colors that make up this pink color, right? And remember that each of these colors represents an electron going from a higher energy state to a lower energy state. Okay, so this is what I said in that video too, that this is like a fingerprint, right? So if we heat up some unknown gas and we see these colors, we can match it up with what the element is. So I'm going to just go through a few of these here with you. This is hydrogen, okay? If we heated up neon, and I do have neon, I just don't know if it's working. I'll see later. But if we heat up neon, it looks like this kind of orangish color, like neon orange, right? Like the neon signs that you see on old buildings and stuff like that. But if you look at it under the spectroscope, you can see it does have a lot of orange and red in it, but it has some green in it as well too. Okay. And then helium, here's another one. I don't think I have helium, but helium looks a little more reddish orange than neon. And if you look at its spectra here, it still has that bright yellow kind of orange and red in it, but this one has a little bit more blue and purple as well too. So remember, each of those represents an electron going from a higher energy state to a lower energy state. Okay. Now, this next part that I'm going to go through is trying to show you some different diagrams that you do in Science 9 and that we analyze in Physics 30. And I usually spend more time on this because you have to memorize this stuff and it can be a bit confusing, but you don't have to worry too much about that right now. So about memorizing and that. So I'm just going to walk you through it. Okay. In this example here, we just have a hot, solid, or liquid, whatever. It's just emitting a continuous spectrum, like our sun. Or here we have a light bulb, and all that they're doing is they're passing it through a narrow opening here just to concentrate the beam, and then they're putting it through this. They're just deflecting it here through this prism here, and also when they put it through the prism, it's also dispersing it, right? So it's causing that refraction to happen, and they put a lens to focus it, and we see a continuous spectrum. Okay, and you guys know this if you've played with if you have any prism, or if you even have any of those sun catchers in your window that like are glass with kind of that are have different etches in them, or different they're cut a different way, even like a diamond ring. um, it causes the light to spread apart, right? And so, just my front, though, the window in my front door of my house here, when the sun catches it, there's a little spectra on the floor, right? And it's kind of neat to see that, right? And whatever, right? People call it a rainbow, but it's a spectra, and it's just basically the white light being, dispersed, right? So that's any continuous spectrum we call. Okay. In the second one here, we have a low pressure gas here. Okay. Um, and we heat it up, we excite it. So this is a heated gas, kind of like what you saw in these diagrams here, right? So we heat up the gas. Now, when we heat it up, it excites it, so it causes the electrons to move to higher energy levels, and then they immediately go back to the lower energy states. And when they do that, they're giving off energy. And that's what we see, is that energy that's being given off. Okay, this is what we call a bright line spectrum. Okay, or an emission spectrum, because light is being emitted from the electrons. Okay, a bright line spectrum or an emission spectrum. You used to have to memorize this, right? Then there's the other one that we have is we can have a cool gas. Okay, so keep in mind with a cool gas that a cool gas is the electrons are in their lower energy state. So if we try and pass a light through a cool gas, the light that we're emitting here, right? Some of it is going to be absorbed by the electrons, the ones that are at the right energy level. So the light that does get through here is going to be incomplete, right? It's not going to have, it's not going to be continuous like this one up here, right? It's going to be missing some because some of those electrons were absorbed, or some of the energy was absorbed by electrons, pardon me. And so what we're going to get, it looks like a continuous spectrum, but there's black lines in there. And wherever there's a black line, that's where an electron went from one energy level and it absorbed that energy and went up to a higher energy level. Okay, so we are missing some of the wavelengths of our continuous spectrum that we would have otherwise. Okay, now something that a lot of people miss in this, and they're, they get a little bit confused that what the difference is that in this one here we don't have a light source, right? We have a gas, right? And these gases are typically invisible. Hydrogen is invisible. We just heat it up, and when we heat it up, the electrons go out to a higher energy level, and then when they go down, they emit light, and that's where the light is coming from, is the electrons going down. In this diagram here, where's my mouse? In this diagram here, we just have we have a light to begin with. We have a hot light bulb here, and we're trying to get that light bulb over here, but we have to pass it through this cool gas first, and the cool gas is absorbing some of that energy and taking out then some of these wavelengths of light. Okay, that's the big difference. Now, what's really interesting about this, and it should make sense if you understand it in terms of the orbitals, is that my absorption line spectrum, and I didn't mention that here, but this one over here, where we have these dark lines, it's called a dark line spectrum or an absorption spectrum because it's the gas is absorbing some of the energy. Okay. Now, what's interesting to note is that if we line up, if we had, they are both for hydrogen, let's say. So this one, the hydrogen was the cool gas, and here we heat up hydrogen. So we have heated hydrogen, and here is cool hydrogen. Okay, and we're passing light through it. What we note is that this heated hydrogen, where we see the electrons going to higher energy levels and then dropping down, we see these bright lines here. They line up exactly with the dark lines of the cool hydrogen that light's trying to pass through. And the reason for that is that hydrogen has those energy levels, right? And we said in that previous video, from the first energy level to the second, it was 10.2 electron volts that's required, right? So if you have energy that is 10.2 electron volts, right, passing through this cool hydrogen, it's going to take one of those, or the electron in the first energy state is going to take that energy and move to the second energy state, and then we're going to lose that, right? And so we're not going to have that energy go through, and you'll have a black or dark line. But when that electron in a heated hydrogen gas, right, when that electron moves up to a higher energy state and now drops back down and gives off 10.2 electron volts, we're going to get that bright line. It lines up exactly in the spectrum because that energy, 10.2 electron volts, if we use this formula here, we can find out exactly what wavelength that is, and that's the same wavelength here as it is down here, right, in the spectrum. It's just that in this one, it's removing that energy from the spectrum, and here it's emitting that energy, right? And so when we look at these graphs down here, you can see for the absorption spectrum, this is intensity. So this is the brightness of the light that you see. You can see that there's these drops here where you see the drops in the light. In the emission spectrum, we see these bumps in the intensity of the light, right? And they're at exactly the same wavelength, right? So they're going from those energy levels. I mentioned in the last video as well too that these are like fingerprints. So if you look at the different elements, hydrogen, sodium, helium, neon, mercury, these are the examples in here, you can see that they all have different combinations of these bright lines. And the reason for that is they have different amounts of energy that are required to go from one energy state to another energy state. And that's a property of the element. Keep in mind that the nucleus is different for each of these elements. So that has a different attraction and pull of the electrons for each of the elements. And so it's all, they're all different. Okay. And hopefully, probably not, I'm not very hopeful, but hopefully you remember this from Science 9. You took these in Science 9 and they gave you this random star, and they had these lines in here, and they say, what is this star made up of? And then you had to go down and you say, okay, this one matches up with here and this and here. So Mercury is in there, and then these ones match up on here, and that's sodium, and so forth, right? And so you're able to match up from that star, which elements make it up. Okay, we're not going to be doing that right now, but we could. All right, so this is it's a famous image, I guess, in physics. What you see in here is something called the Fraunhofer lines, which is a really awesome name, Fraunhofer. Um, it looks like a continuous spectrum, right? Except there's all these black lines in there, right? Now, this is from the sun. This is from the sun. Why don't we have a continuous? Why don't we see everything in there? Well, think about from the sun. And this is a highly scientific drawing, by the way. Oh, his eye's a bit droopy. I think he might have been doing some illicit drugs. Okay. All right. That's his tongue there hanging out because he's lost control of his motor functions. All right. So the sun, the energy from the sun has to get to the earth over here, right? And in space, there are gases that are around. Okay, these gases that are around that it has to pass through. And then there's a bunch of other gases that it has to pass through. Oh, this is awesome. Called our atmosphere. And it has to pass through, it comes to the surface. So passing through these gases in outer space, and then the gases that are in our atmosphere, right? Not all of the energy from the sun reaches us. Obviously, we don't get the UV radiation that comes from it, or most of it, and then the other radiation that's more harmful as well, we don't get from the sun. But even the visible, which would typically our atmosphere allows all the visible to get through, because of the different gases that are in the atmosphere, we do lose some, right? The gases absorb that energy, and it causes the electrons to be excited, but those electrons then are all associated with specific wavelengths. So you can see all these dark lines in here. These are all associated with that energy that's being absorbed from the sun before it reaches the surface, and these are called the Fraunhofer lines. Ta-da! This diagram is kind of showing you that as well too for this distant star, and we have a satellite here that's trying to see the distant star. It has to pass through these different gases. Each of these gases is going to absorb some, and we can see that absorption in this spectrum here, right? And then we can determine what gases that the light passed through based on that. So we get all this incredible information from these satellites, and it really boggles my mind. It really does when you think about how far humans have come in terms of technology and stuff like that. But to really figure this kind of stuff out and to create satellites that are able to detect this stuff, and for us to say this cloud of gas that's millions of light years away is made up of this element and this element, it's just completely amazing. It's so awesome. I just every time I think about it, it just blows my mind away. It's crazy. All right. Let's see here. A continuous spectrum is due to the interaction between the close packed atoms. In a low pressure gas, the atoms are very far apart, so any light emitted is from isolated atoms. So that helps to explain a little bit more about some of the problems that arise from us talking about looking at these spectra. We're not going to get into that in great detail today, because we need to 30%. We talked about this already with hydrogen, so I'm not going to go over that. This equation, again, we don't have it anymore. You used to have it. If we went to the U of A for our field trip, which I'm sad that you guys don't get to go on, which is one of my favorite parts of Physics 30, is being able to take you to the U of A and kind of show you around a bit and then do some labs there. They make you do this equation in that lab. And basically what you're doing is you're trying to find the wavelength of light. In here is Rydberg's constant, which is right here, 1.10 times 10 to the 7. And then this is just the energy levels. So if your final energy level is energy level 2, and your initial energy level is energy 4, then you put those in there and you can find out what wavelength of light you have based on this. So it's a very straightforward calculation if you think think about it, there's a constant in there, and then we're just doing the inverse squared of these energy levels, and that gives us the inverse of the wavelength. It's quite remarkable itself that we can determine what the wavelength of light is based on that as well. Okay, now the visible lines again are from the Balmer series, and if you remember that from last video, that is when we end at the second energy level. Okay, if we end at the first energy level or the third energy level, then they're infrared and ultraviolet, and so we wouldn't see them. Okay, and this is a similar diagram to what we saw in our last video as well too. So in our last video, I talked about that you might see a diagram like this where it has 0 here and then 13.6 at the top. So this one is just showing you now the values over here is the amount of energy from the ground state. Okay, so obviously at the ground state, there's no energy. You know, in the second energy level, you're 10.19. We had it rounded to 1 decimal place, so 10.2 electron volts, etc. It's these ones that give off energy between 700 and 400 nanometers, right? And so we can actually see them. But we have these different series that, you know, if you end at the third energy level, it's called the Paskin series. If you end at the first energy level, it's called the Lyman series. Okay. A couple other things on this diagram. When we're going up on here, we're absorbing energy. So that's what this is saying. And then we go from a higher energy level to a lower, we're emitting energy. We're giving energy off. Remember, you have to lose energy to go to a lower energy state. You can't visit the lower energy state with a lot of energy. Okay. The Balmer equation only works for hydrogen. So that's what we look at. So we're going to do a couple examples here, and I think that's it, yeah, for this lesson here. All right, so I mentioned earlier in the other video as well too that you used to have to come up with this diagram yourself with the radius and the amount of energy, but now we give you these diagrams, so you just have to do a few calculations. Pretty simple calculations, if I must say so myself. Okay, so example 1A, energy change in moving to the first excited energy state from the ground state. So we're just going to this one right here. Now, it's a little bit, you know, it's kind of wordy. The first excited state is actually n equals 2 because our ground state is not called 0, it's called n equals 1. So it can be a bit confusing. So just keep that in mind when we're doing that. We just want to find out the energy change in moving to the first energy state. So we just subtract these two, right? And we did this one last video already. Take away 3.4 electron volts is 10.2 electron volts. So that's the energy change, 10.2 electron volts. Okay. The energy change in moving from n equals 3 to the ground. So n equals 3 to the ground state. And I should say in here that we actually lost 10.2 electron volts when we're going from here, or we didn't lose it. We gained 10.2 electron volts. We had to absorb it. In this one here in B, we're going to lose this energy from going from n equals 3 to n equals 1. Okay, so we're going to take 13.6 again, and I'm going to subtract 1.51. Okay, and that's going to give me my value here. So let's see here. That would be what? 12.09. Is that right? I think so, 12.09. So that's the amount of energy that would be given off if you go from the n equals 3 to n equals 1. Okay, let's move my head out of the way again. Determine the wavelength emitted by a hydrogen atom if n equals 1 and the final is n equals 2. Okay, so we're going from here to here. So this is a visible one, right? This is in the Balmer series if we're ending at n equals 2. So now I'm going to do 3.4 subtract 1.51 electron volts. Okay, so if we do that, that would be 1. Oh, why do I do this to myself here? So if we subtract this here, 8, so 1.89. Okay, 1.89 electron volts, right? Now we want to find the wavelength, so now we have to put it into this formula. E is equal to hc over wavelength, or wavelength is equal to hc over energy. Because it's in electron volts, use Planck's constant for electron volts. I might as well show you this, why not? All right, so let's put that into the calculator here and calculate it. So that's 4.14 to the negative 15 times 3 times 10 to the 8. And that's divided by 1.89. And that gives me 6.57 14 times 10 to the negative 7, which in terms of this here, it's off by a little bit here, but I have a feeling that they were using not this chart in here, but they were just using 1.5. So if I do, I'm just curious, but let's just see if I do 4.14 to the negative 15 times 3 times 10 to the 8, right? And if I divide that now, instead of by 1.89, I just divide it by 3.4, take away 1.5, which would be 1.9. I'm guessing that's what they did here. No, then they get 6.54. So I don't know. They must have been using a slightly different value, or actually, this is a good time to talk about this. Whenever you're using electron volts, if you take electron volts and then you convert it into joules and then use this calculation in terms of joules, the Planck's constant in terms of joules, you're going to get a slightly different answer because it's a rounded answer. So I'm guessing, and I don't want to go through that calculation on here because this has already been long enough, this video, but I bet you what they did is they found this 1.89, excuse me, then they converted it to joules, then they plugged it into this formula here, but they used Planck's constant in terms of joules, 6.63 times 10 to the negative 34, and then found the wavelength that way, and I bet you that's why it was slightly different. There's a slight difference. And so if you were doing the diploma exam and this was a numeric response, they actually have both answers as being correct because you can do that. You can convert to joules if you want, but it's just extra work. Okay. Now, what's interesting about this is that that's 655 nanometers, right? And so 655 nanometers is in the visible spectrum. And we know that it should be because anything going to the second energy level is in the Balmer series, which is in the visible. Okay. All right, let's do the last example here. Now this relates to what I talked about at the end or near the end of the last video. Now, I'm just going to review that because it's a really important point, but if I have an electron, and in this one here, it says an electron in the ground state. So I'm going to put in the ground state here. There's two ways that this electron can move to a higher energy level. It can absorb electromagnetic radiation. If it does that, it has to have the exact amount of electromagnetic radiation. So for this one here, it needs 10.2 electron volts to get to the second energy level. It would have to have exactly 10.2. If it had any bit more, any bit less, nothing would happen. The electromagnetic radiation would just keep going through when nothing would happen. Okay, so that's one way of that happening. Okay. Now keep in mind that that's very, very rare that that's going to happen, right? To have electromagnetic radiation of an exact amount striking that electron at that given point in time, right? So this doesn't happen all that often, right? This is more likely to happen is to have electrons, free electrons passing by with kinetic energy that hit them. And if you do that, you don't have to have the exact amount. You just have to have at least that amount, okay? Now, it says that this electron has 10 or 12 electron volts of energy, right? It's going to give it as much energy as possible. So it might not even go to the first energy, this first excited state. It might have enough to go to the second or the third. So we have to kind of determine that, right? So what we need to do in here is it says what is the highest energy level that the energy the atom could attain, right? So what we need to do here essentially is just take 13.6 and subtract the 12. So let's say that it could take all of it. What would we be left with? We'd be left with 1.6 electron volts. Okay, so if we look at let me see here. If we look at this first energy state here, we would need to have 10.2 electron volts. Okay. If we go to the second energy level here, we'd be going from 13.6 and then subtracting the 1.51. Okay. And we did that over here. I'll just show you here. 13.6, take away the 1.51, that's 12.09 electron volts. Okay. And we only have 12 electron volts. Okay, so we can see that it doesn't have enough energy for it to actually go up to this energy state. It would need 12.09 and it only has 12.0. So it's only going to go to the first energy state or the first excited energy state here. There's another way. I'm sorry, I know I said to subtract that there, but there's another way of doing it, but I just decided against. Erase. Okay, so it takes 10.2 electron volts to go from here to here, and then it would take 12.09 to go from here up to there, which we don't have. We only have 12. So what's going to happen is this electron that's here, we have this electron that's coming by, it's going to strike this one, it's going to give it 10.2 electron volts. So then we have 12 electron volts, subtract the 10.2 electron volts, which is 1.8 electron volts that's remaining. That 1.8 is going to be still with this electron, and it's going to have it as in terms of kinetic energy. And that's what this is saying. And what would be the resulting kinetic energy of the electron that originally collided with the electron in the atom? Well, this electron will take 10.2, will go up to this energy level, and that'll leave the other one with 1.8 electron volts of kinetic energy. And you could determine what the speed is by putting it into 1/2 mv squared, but just make sure that you convert that to joules first if you do that. Okay. And that's essentially it for this lesson, okay? What we basically do in here is we take a look at these different energy states, right? The difference between them, calculating them, so subtracting the numbers on the side here to find out the amount of energy between them. And just the theory part of that, understanding the two methods by which electrons can go from one energy state to the other. The other parts in here that we would focus more on in, if we had the diploma, would be talking about these absorption and emission spectrum, and just making sure that we have a really good handle of the difference between those. Okay. I am going to make you a quick little video, a demonstration video, but all that it's going to be is just showing you heating up these hot gases. And so the video is, not really all that spectacular or anything like that, but I just wanted to demonstrate it for you because we do that in class typically as well. Okay, so that's it for this week. I would have maybe pushed and done another lesson. I know I'm only supposed to do 30%, but you guys are doing the chat unit 3 assessment as well too. So we'll try and keep a few less lessons this week. Next week, we are going to be talking about why the electrons only exist in each of those energy states. So we're going to answer Bohr's problem. And we're also going to take a really weird turn. Okay. We talked about how particles can have waves can have particle-like properties, right? The whole quantum thing. But a scientist is going to ask the question, is it the other way around as well too? So can we look at a particle and see wave-like properties of a particle? In other words, can I see a particle and can that particle have a wavelength? And I think you know where this is. I think you know the answer to that because I said it's weird. The answer is yes. So we can find this. Is called the de Broglie wavelength, and we can determine what the wavelength is of a particle. Keeping in mind, though, and I don't want to teach next week's lesson yet because this video is long enough. But keeping in mind that we're talking about quantum, so it has to be really, really small, moving very, very fast in order for it to exhibit wave-like properties. So some weird stuff that we're going to look at next week. Then the week after that, we're going to go look at some really more nuclear stuff. So we're going to look at nuclear fission and fusion. We're going to look at radioactive decay. I'm not going to spend a lot of time on that, though, because you do that in math. So that's one of the sections I'm going to kind of skip. We're going to look at something called mass defect as well too, and that's where energy is converted into mass and mass is converted to energy. So E is equal to mc squared as well. Okay, and then the last week, which is going to be no assessment, we're going to look at the very last topic in this unit, which is talking about subatomic particles, quarks, and the Standard Model. And, we're not going to spend a lot of time with it, and we usually don't spend a lot of time with it because, to be completely honest with you, this is where we're at in physics, like in the world right now. And this model that we teach at the end of this unit is actually falling apart. Okay, they're finding new particles, they're finding things that contradict it. So we're going to talk about it a little bit and how they came about it. But to be honest with you, it's not solid right now. So we're going to just spend a little bit of time, not assess anything, but just a little bit of theory with it. It's kind of interesting, and talk a little bit about string theory there at the very end. And yeah, that'll be it. Summer break then already. Can't believe it. So I will talk to you guys soon. If you have any questions about any of this stuff or the assessment, the review, or the assessment, the quiz, exam, whatever you want to call it, for Unit 3, just make sure to ask, okay? And I am here for you. See you soon. Talk to you later.